All right, let's get started. All right, so a quick review of what we were talking about in the previous lecture. So we start talking about the first chapter, right? So introduction to data mining. So the key things are, okay, why do we care about data mining? What is data mining? What do we do? Some of the major issues, okay? So quick review of some of the questions we covered. First one, data mining pipeline. If you remember that figure we had, the black box, right? On the one end is the data coming in. The other end is knowledge. That's what we're trying to do within the black box. So what are the key components within that black box? Anybody? Data transformation. Okay, let's start from the raw data. When you have the data, what do you do first? Cleaning. Okay, a little bit just understand your data. Okay, see what kind of data you have, how you're getting the data. So that's the very bottom left. You have the blobs of data coming in, okay? And then, we do the cleaning, we do transformation, integration. Those are all things about pre-processing, right? What happens next? Somebody mentioned it? Warehouse, okay? So we'll be covering data warehousing. So that's a way of kind of organizing your data. But more important is about kind of preparing the data so that you can do the next step, which is modeling, right? Okay, when you have the data ready, they're properly cleaned, prepared. So now you have the specific subsets of data that is needed for your particular modeling process. Okay, so when you have the model, what do? Evaluation. Okay, think about how you evaluate your model to demonstrate that this model is correct, it works, it's more efficient or better than existing solutions, and how it is good enough, right, for the kind of problem you have. Okay. So that's a pipeline. Just always keep that in mind, right? Whenever you're talking about your data mining project or you're explaining to other people about what you do in data mining, think about the whole pipeline, okay? And then we were talking about the different views, okay? So that's also very important, right? Because whenever we talk about data, of course, I need data, okay? But beyond that, mining, right? How you do mining. So there are a few different views, okay? So we're talking about data, knowledge, method, application, okay? So naturally, you may think, okay, I always start with the data. Sometimes no. Sometimes you start with your application or your problem setting. You say, okay, I need to solve this problem. What kind of data I can get to solve that problem, right? Or sometimes, oh, I'm so interested in this new classification method. I want to test it out. So you may have a method, right? And you want to see how it works in different settings. So that is all fine, okay? But you need this combined view of those four aspects so that you can have your problem defined. Okay? So we're starting week 2. Okay? I know everybody just still getting settled in navigating the whole new semester, but keep in mind we have our proposal, which is coming up in week 5. Okay? So not that far away. And this is really the time I want you to start thinking about your project, right? Find your teammates, start talking to people. But as you're talking about what you would like to do for the course project, right, think about those things, right? What kind of data you may have access to, what kind of problems you're interested in, what kind of knowledge you're trying to learn. Method, I said the method may come later, right? At this point for the proposal, you don't need to spell out all the method, right? But it's more about, I have my problem, right? This is what I like to do. Okay, and how this could be useful in the particular application scenarios, okay? So keep all this in mind as you're starting kind of brainstorming about your project ideas, okay? And then interestedness, right? Data mining will say, okay, find an interesting pattern from your data. Okay, what is interesting? Any of the metrics, anybody remember? Velocity? This is about measuring, like if I find I have, through my process, I found some pattern. How do I know it is interesting? How do you define being interesting? Unique, right? So unique in a way that's like previous unknown. That's one. Anything else? What's the starting point? What do you do in the evaluation? First, you want to make sure it's correct, valid, right? So whatever pattern you found, is okay, it is a valid pattern, it is unique or previous unknown, and? Sorry? Value, potentially useful, right? And there's one more. Not accuracy. Can you explain it? Right? So if you give me a pattern, right? Like you say, okay, this pattern works well, it has 99% accuracy. Great, right? But if you are to apply it in a real world setting, so we want to say, okay, eventually or potentially explainable so that we can understand like why it works in this way, okay? All right, we also talk about some of the major issues. Some of those are really technical, just like what kind of techniques you can use for what kind of problem settings. Because you have different types of data, very different types of knowledge you're trying to learn, so they have all kinds of challenges. You will come up with mechanisms that is working for particular scenarios, okay? So we, of course, will spend the whole semester covering some of the core techniques and also really highlighting the characteristics, right? Why you want to use this method for this kind of solution, for this kind of problem, or why this solution may not be good for those type of problems, okay? We kind of like ended here, but I want to just still like spend a little bit more time talking about like data science ethics, okay? So many times when we just work on the data mining project, the key challenge is about getting the data, right? So we say, when I have the data, then I can do whatever I can. That's great. My problem is solved. But no, actually with the data ethics, this actually really governs everything you do with your data. Okay? Think about who has the data. Where do you get the data? How do you collect the data, right? Who gets to use it in what way, right? And then once you have, say, developed some method, are you sure that this method is fair or is like not generating bias in your process? Also, when you have your pattern, when you have your results, is it used fairly? What kind of impact it may have, okay? So think about all those aspects, okay? This is important, not just say in the course project setting, sometimes also this is course project, why do I care, right? But you will see like all those actually can have sometimes like unintended like impacts, good or bad, right? So always think about like when you're working with some kind of data, when you're doing something with the data, when you're interpreting your data in some way, or when you're using the results of your data mining project in a certain way, what kind of impact you have, right? And how should actually really make sure that you're not generating some unintended like negative impact, okay? First part, ownership, right? We all care about our privacy, right? We don't want our sensitive data to be used or disclosed in a certain way, okay? So starting point is really about like who owns the data, what can you do with the data, okay? So a lot of times think about privacy, think about anonymity, okay? Because many times with the data mining, the goal is to find general patterns, right? So there are actually quite a few like research and applied solutions trying to protect the privacy while learning some useful patterns, right, from a general data set. Okay, so that's also very important given the problem setting. Okay, for your model like data model validity, okay, but more important is about this bias. Okay, so there was an extreme example from one of the like colloquial talks. Okay, so so basically in that particular case, like they were trying to build a model to automatically grade. I think this was high school like essays. Okay, so somehow the data set they used, right, had like black students all having lower grade. Okay, so somehow like if you're not careful, you can imagine how the model would just take all that information and use that like ethnicity and say, okay, black students like tend to get a lower grade. Is that fair? No, right? You shouldn't be using data set in that way. So because why would the quality of essays associated with who I am? It should be the quality of the work itself, okay? So those are things like sometimes just easy to do if you just applying existing model, but really think about, right? What kind of information you're using, what kind of data you're using, what kind of techniques you're using, right? And whether they're actually protecting some of the some sensitive information and not generating biases, like unintended biases, okay? The last piece also important, right? Sometimes you say, okay, I build a model, it works well, has high accuracy, great, I can use it, right? But how do you interpret that, right? Sometimes you say, okay, the fact that you find a pattern and then you interpret it, again, just using my, the black student grading model. If you use that, the model works, and then you say, oh yeah, now I have learned that black students get a lower grade. That's bad, right? That's really bad, right? That can have even you may not intend for that to happen, but the way you use it or just not being careful with that process and the way that it's being used in the actual way, then the interpretation, the impact can be really bad, okay? So I just want to stress this importance, right? Because data is everywhere. You can probably get data in many different ways, right? And you can do whatever. Nobody really is controlling what you do with the data, right? But think about the potential implications, okay? And always discuss, right, with people, okay? Think about what if, or what would happen if I do this, or what if I interpret my data this way, or my results in this way, okay? So throughout the process, right, and of course for your future career, just always think about this. And of course, during the semester for your project, for any data-related problems, if you have questions, concerns related to the ethics aspect, feel free to talk with us, and we're happy to provide more information. Okay, all right. I want to add another slide. This is about confluence of multiple disciplines. What does it mean, right? Every time when I start talking about data mining, people say, oh, how is it different from machine learning, right? And also say there's a lot of statistics information. There's a lot of high performance computing as well, okay? So this is not a complete picture, because you will see data mining is really interacting with many, many different disciplines, okay? Why is that way? Well, starting point, right? We want to mine something useful from the data. We may have very different tools that we use, right? And then they may have very different capabilities we can leverage. So here we just look at some of the examples, right? Apparently, machine learning is heavily used, right? I always tell people that I don't do research in machine learning. We use a lot of machine learning methods in our research, but I'm not a researcher focused on machine learning. What does it mean? Right, you have techniques that we can use in our modeling process so that we can gain knowledge from our data, okay? But also natural language processing. Some of you may be working on projects that are related to natural language processing, right? You'll be using some of the techniques there, using some of the knowledge there. That's great. But it's from the data mining side, it's about mining from text data, right? Okay? And then database, of course, database actually was that a foundational thing, because before you can work with your data, there was a lot of focus in terms of how you manage your data, right? So a lot of research goes into database management, relational database, and also later on distributed, scalable database, and NoSQL. So there's actually a lot from the database side, okay? Social science nowadays, right? So for example, we do other research from the online social media. Okay, so we're trying to understand various kinds of behaviors by individuals, by groups, or general topics, all that, right? So we may be using some of the natural language processing methods, but also how we interpret that and how that connects back, right, to the general population we're studying. That also connects back to social science, okay? Another one, high performance computing, okay? That really goes into the efficiency side, right? As we said, right, data mining tries to leverage a lot of data, okay? And to handle that, we really look at how we scale things up with a lot of information and still do it in an efficient way, okay? So leveraging whatever advances, right? Cloud computing, high performance computing, or in the distributed fashion nowadays with the mobile systems, right? That's also what we care about. So as you can see, right, when you talk about data mining, it's not just say, okay, this is the field and anything else is not data mining. Rather, it's in data mining, what fields or what skills or discipline we may be able to leverage, okay? And there's a lot of interaction. All right, a little bit more information. So this is about where to find data mining resources, right? Well, of course, we have the textbook. We will be covering quite a lot of information throughout the lectures. For your course project, of course, you're welcome to, actually, I encourage you to search online. There's a lot of information there, right? Data sets, tools, tutorials, or, of course, existing research papers. So there's a lot of information you can leverage. But there's one I'd like to really highlight. This is a KDD. So it's ACM, so that's the SIG-KDD. So that's a special interest group in knowledge discovery from data, so KDD. Okay, so if you search on KDD, that is actually the, I would say, top venue, conference venue that we have in our field, okay? So it is an annual conference. Every year, like they have basically a list of, a lot of information that's happening there. So it's a conference. If you go to the website, okay, you can find a lot of information. Every year, they actually have tutorials, okay? Tutorials actually are very nice. I like the tutorial. They have some very state-of-the-art topics that is actually very nice kind of starting point if you're interested in getting into a particular area related to data mining, okay? Of course, they have the core research tracks. So that's a lot of the really frontier research that's happening in the field, okay? I also like that they have this applied data science track, okay? So as the name suggests, it's more applied, okay? Many of those actually are real-world systems or real-world solutions, okay? Leveraging a lot of data for some interesting and challenging real-world problems, okay? KDD Cup is like a competition, okay? So that's also like if you check out every year, like they almost every year they have this KDD Cup is a competition. Basically, it's more like a better formulated problem setting, but actually really have some kind of challenging problems related to data mining. Okay? I also list the sponsors. If you're interested, always check out the sponsors. Why do you care? Why do people sponsor KDD conferences? Because they want to recruit, right? Or they have things that they like to showcase to the community. So sponsors actually also very interesting. Always check out who are sponsoring those events, and so you actually get a sense of what kind of data mining research related work, right, they may be doing or are interested in recruiting students for, okay? I have a longer list of related conferences. Those are all they have pieces of data mining research happening, okay? So if you're interested, definitely check out that as well, okay? So later on, as you're doing your course project proposal, I ask you to do a bit more related work, right, literature survey, okay? So you don't need to do exhaustive research, but at least check some of those venues so that you know those venues have related work that may be useful for your project, okay? All right, so this is a pipeline we'll be following, and today, after the introduction in chapter 1, we're going into the next one, chapter 2, okay? So now we're just getting started. So when you get to starting point, when you have the raw data, okay, so you want to understand your data, okay? And then try to do some pre-processing, okay? So that is what we're going to cover in chapter 2, okay? Starting point, data, right? Measurements. So you have data, understand what they are. You do some measurements to get some general understanding of the characteristics of your data, okay? And then now you start pre-processing. That's when you actually modify, right, data, okay? All right, so we're going to cover actually quite a few items, okay? So if you're using, say, the 3rd edition, and if you compare with the 4th edition, you may have seen, actually, this is a combined one. So in the previous version, they had chapter 2 is only about understanding your data. So that's really the first 3 is about data, statistics, and then some similarity measures. And they had a separate section on pre-processing. So now we're combining that into one, okay? The content is mostly similar, but they have some update. So if you had the older version, make sure you check at least the newer version of some of the discussions here, okay? But as you look at the flow, start by understanding data, right? What kind of data we have, right? And then we're trying to look at some of the statistics of your data, okay? And then discuss, okay, given my data, given the different types of data I have, how do I measure similarity and dissimilarity? Okay, that is, again, a core concept in terms of data mining, because we're always talking about what's similar, what's different. So you can group things, you can differentiate things, right? Okay, and then when we get to the pre-processing, components. We'll talk about quality because that's the starting point, right? Why do you even need to pre-process your data? Because there are various kinds of issues with real-world data, okay? So we'll talk about quality, cleaning, integration, transformation, dimensionality reduction. So all those are just ways that you need to prepare your data, okay? So get your data ready so that you can use it for the downstream analysis. All right, starting point. We touch upon this in chapter 1. We just say, okay, when you talk about data, right, think about your data view, right? How you describe your data. What type of data you have, okay? Starting point, what is it? Right, this is a data set about, like say, campus students. This is a data set about different types of vehicles. This is a data set about like online social media, people talking about some particular topics, something, right? You have a way of describing what data is. But then there are a little bit more specific, right? Because the data or data sets come in different formats, okay? So earlier when we talk about like a natural language processing, we have text data, like document, right? But many times, starting point database, right? A lot of times, database was organizing data in some kind of records, right? Relational database, naturally, you have those columns, you have rows, talking about like information about the different like objects, okay? And then you have graphs and networks, right? We show some example, like you could have transportation networks, the actual computer, internet, right, networks. You could have the power grid. You could have like a molecular structure, or like I think it was protein structure. It's a 3D or this 2D, whatever. So you have a way of networks or graphs that is describing relationships, right? Also, you could have information that are ordered, right? So this is like the sequential information, right? With or without time, okay? So you can have time series of data. You can have just general sequential information. You could have the occurrences of things, right? They are ordered, but they may have like either fixed intervals or you have some kind of different intervals, okay? Spatial, image, multimedia data, okay? So those are just to give you a like, general idea about when you talk about data, think about what types of data you have, right? How you get the data sets and start working with it, right? Are you reading in your data like a data set that has just like a CSV file, you have the columns, rows, or it's images, or audio files, or something, okay? All right, now you have your data set. Okay, so now let's dive in, right? So there are a few terms. So we say data set is just a set of data objects, right? Because within your data set, you're describing some information, okay? So here, my objects, right, can be related to, say, students, courses, departments, degree programs, or this could be describing a particular location or describing a particular event or something, right? So you know a set of things, okay? So objects, right? So data object, that's really the entity we care about, okay? So if you say you want to find some patterns, right? So that's about like the students, okay? Or I want to figure out like which kind of like events are more popular, okay? Or like if we talk about different products, right? What is more popular? Or you're talking about your customers. You're talking about transactions. So those are the objects, okay? But when you have the objects, you need a way to describe them, right? So now you think about, again, in the simple like a CSV format, each row is your object, right? That's one object. But now to describe that object, you need some columns, right? Those columns are the attributes, okay? So we sometimes refer to as like features or descriptors, whatever. But it's really about some way to describe your object, right? Okay, and now, so we talk about data sets, object, attribute. But now attribute type is something that we'll be paying more attention to, okay? So what do we mean by attribute types, right? Because there are different ways for you to describe an object, okay? So what we call nominal, or sometimes referred to as a categorical, it's just a few kind of finite number of descriptions, okay? So you think about the major, right? That's a simple one, right? So like if you look at the whole campus, we have students with many different majors, okay? Right? So, but there's a finite number, okay? And that is the, like, say, you may have like a few, usually it's like descriptive, right? Some kind of like semantic understanding if you look at the name, okay? If you say the name of a city, right? Or it's like a make and model of different vehicles, right? Those are all nominal or categorical values. And then you could have binary, right? As the name suggests, right? We work with binary. Binary is whatever, 0, 1, yes or no, true or false, right? So basically you have two potential values for that attribute, okay? So instead of like, say, asking a student about, say, what's your major, which is a nominal attribute, I could say, is the student see as a major or not? Then it's a binary attribute, right? So depending on your problem setting, you may say, okay, yeah, if my setting is more about it's a CS or not, or actually I want to know different majors, then you'll be using nominal versus a binary, okay? And then ordinal, okay? So this one is ordered. Remember earlier we were talking about ordered data, okay? So ordered data could be, say, like individual transaction. That is ordered by the object level, okay? But now if you talk about an attribute, so attribute can be ordered because the attribute values, right? So think about all the different types of ranks in different settings, right? Or like, say, the vehicle size class, that's another one, right? So you have, again, a few kind of like attribute values. But how is this different from the nominal one? Nominal attribute versus ordinal attribute? Yes? Not ordered. Like, for example, when we talk about majors, right? How you order like CS major, electrical engineering, history, physics. So they're not ordered, they're just different, right? Okay? Well, if you're talking about ordinals, there is an order, right? So there's a natural way of ordering the values. So if you see a value, not just value itself, you know if you're comparing two values, right? So not about just they're similar, the same or not, it's about the order, okay? And of course, we're all familiar with the numerical values, okay? Numerical value, of course, is broadly used in many settings, okay? Think about your, like, a lot of the nowadays sensor readings, right? They're numerical, right? And then if you talk about, like, say, number for, how to say this? If you talk about sales, right? Transactions, you always have like the amount, like the revenue or the actual price or the stock price of something. So there's more of the quantity, right? That we're trying to utilize, okay? Now, because they're different, okay, so apparently we treat them differently, right? So that's why many times it's important for you to say, not only say, okay, I have like a data set with 1 million objects and say 100 columns. You need to look at the columns or the attributes and understand what they are, right? Because different attributes mean different things, their values are different, and you use them differently. Okay, so here a little bit more examples about the actual numerical attributes, right? So when you have numerical values, okay, so easiest thing is just to compare, right? Not only say whether they're the same or not, which one's higher than the other, okay, or how big the difference is, right? So they're just natural ways for you to look at, okay? But there's also this difference between interval scaled versus ratio scaled, okay? So the term may be a little bit confusing, but if you look at the examples and think about the true 0 point, okay? So for example, like say if you have, I don't know, actually today I do have, sometimes I see quite a few water bottles, right, in the classroom left over. So I've been counting how many water bottles I have. So that's the actual like value, and there's a true 0 point, right? Because if there's a none, it's an actual 0, okay? And every time you get one more, then it's actually you're counting from the true 0 point, okay? But if you look at some of the interval scaled, okay? So currently it's year 2024, okay? So does that mean year 0 is the absolute 0? No, right? So it's relative, right? So you basically have, okay, so this year from the next year, so the year is the same interval, but you don't have a true 0 point versus the ratio scales, there's a true 0 point, okay? So that's why you can do this ratio comparison. So it's like if I have $200 and somebody has $1,000, right? So that can be, say, okay, 5 times more, okay? But say if, say, year 200 versus year 1000, that doesn't mean that like you have like 5 times more the time, the time, right? So that, again, a small notion, but the way you use it is different because you have either a true 0 point or you don't.
So,
yes?
when we normalize interval scale, it automatically becomes basis.
Just pick up a little bit.
When you normalize interval scale, it will be basis.
Okay, so the question about normalization, of course, we'll cover that later. Okay, that depends on what you're doing with the normalization, right? So that's why I say with the ratio scaled, yes, because you are multiplying, dividing, and that actually would be okay for the ratio scaled. That may or may not be meaningful for the like interval scaled. So we just keep that in mind when you do that. But knowing that there's a difference, right? So that's what I say, knowing the properties, whatever operations you do, because now you're changing from the raw data, right? So after the raw data, whatever you do, every step you do, think about it, right? Is it what you intend to do? Is it meaningful for the different types of attributes you have and for the values they have, okay? Another one, discrete versus continuous value. That's, again, something you will naturally like encounter, right? Think about, again, money, how much money I have, right? So you can use the dollar amount, so you can say it's an integer value. But then if you get into some of the, say, average or divided, so like your annual income with a tax rate or whatever, you may get point something, right? Okay, or the stock price, okay? So you can see, right, when you have discrete value versus continuous value, and sometimes if your operation, say, this value can only be discrete. So if your average or mean calculation gives you a like non-discrete value, you need to do rounding, right? Okay, rounding up or rounding down, does it make sense for your problem? So all those are things you want to consider, okay? So at this point, we just say they're different, okay? But you're already asking questions like, knowing that they're different, what do we do afterwards, right? Or require some kind of reasoning, okay? All right, so say this is data, right? So far, we haven't done anything. Right, we haven't changed anything, right? We just look at the data, okay? So next one, okay? So I know what kind of data I have, what kind of attributes I have. I know there are different values in my data set. The next step is about measuring. So you're trying to characterize your data, okay? So I have a data set, right? So a lot of time we'll talk about some of the statistics, okay? So the general idea is that, okay, I have a data set. Can you tell me like what they are? Or what kind of general patterns. This is actually already your starting point about understanding your data and trying to learn something from your data, okay? So I want to understand my data, right? So for example, if I get the sales data, right? I know in my sales data I have like at any time points it's about somebody, a customer purchases some item at a particular location, and this is the price that the customer has purchased or something, right? Or if you look at, say, the number of likes, okay? So if you post something, or you're looking at what is the trending online, right, on a particular platform, then you look at maybe the number of likes, okay? So you know there's a particular value, right? You know what kind of value it is, but you don't know what's the average, what's like some kind of characteristics, okay? So for example, like, I don't know the latest, like, if you think about the number of friends you have in a social network, okay? So what's the like average number of like friends you have? Anybody? Hundreds, thousands? Hundreds, maybe? Maybe some of your, if you're popular, you get thousands of friends, okay? But that's typical, right? But you know the extreme values? Highest? Millions, billions, right? If you look at organization, look at some celebrity, so that's again like just some understanding about, like even though say the number of likes or number of friends or number of connections is the attribute of value you're looking at, but the properties, right, is what we're trying to understand. Okay, so starting with the basics, right? You have a data set. Start with N. N is what? Number of objects, right? You have a data set, okay? Starting point is how many objects you have. That's what I used to ask. Like, I want you to have a sufficiently large data set, okay? So millions, right? But do you have, so if you have thousands of data points versus millions of data points, that's the very basics, okay? And then min max, right? This, of course, is about numerical value, right? So you have, like, say, attribute that is numeric, and then you have the values of that particular attribute. So naturally, ask a min and a max, okay? So if you're talking about my number of friends, it could be like min is 0, but the max can be a huge number, okay? But then naturally, then you ask for this other thing, which is a central tendency and dispersion, okay? So you don't need to memorize all these terms, but we get to that, and of course you have slides to check later. But at a high level, it's just like you want to look at the central tendency, just like what is more typical, right? Versus how big things, like how different things are, okay? Because if you look at a particular data set, you look at a particular attribute of value, not everybody is the same. Usually you see diversity. If everybody is the same, then it doesn't matter. I say we all have the same age, we all have the same number of friends, we all have the same like sales value. That's one is not like realistic, but also it's not very useful in terms of mining if everything looks the same. So it's about the difference, right? But when you have differences, then you should say, okay, what is more of the norm and what is more of the extreme, right? Okay. So let's look at some of the specific metrics. Mean. This one you probably have like worked with in many different settings, right? So many times if you look at like a few different values, the mean value is basically the app, like your AdSense app divided by the total number, and that's your mean value. Simple, right? In the real world, you can even do weighted, right? So weighted arithmetic means that means I have the individual values, but they're weighted differently because some values either they're weighted by, say, the frequency, right? So like I may have like the, what would be a good example? So if you have like different, the number of friends, let me use the number of friends again, okay? So I have, say, a population of 1,000 people, right? And then I'm asking how many friends they have, okay? So you could see like these ones are different. You have the individual 1,000 values. You can take that as an average, okay? Or you can say, okay, but those friends are different. Some of them are more important, okay? So now you can add their friends' weight, okay? So like I only have 10 friends, but those 10 are influential versus your 1,000, right? So then you're actually trying to put in some kind of weighting mechanism so that you do the weighted sum divided by the total number, okay? And also this trimmed mean, that's basically you have extreme values, okay? So I don't know how often you see like, say, I think like gymnastics, right? When they do the scoring, right? The judges give the scores and usually they would remove the highest and the lowest and then you take the remaining, do the average. That's just a simple example, right? You want to kind of like reduce the impact of the extreme values, pulling the, your mean values, okay? Median. Median is simple, right? So mean, that's to say like if you take a mean value, that's like arithmetic mean. So that means it will be a value that may or may not exist in your actual data set, okay? Median, right, is something that is like, in a way, if you take the like sorted away, you basically just say, you visualize it's really the middle point, okay? So think about the annual income, right? So if you take, let's say, annual income of a population, so you can easily sort it and then look at the middle point, okay? Of course, if you have like a odd number, right, that's easy, the middle point, okay? And then they have ways, if it's not a like odd number, of course, you need to take the, so like in the middle, there's a left point and there's a right point. So you're trying to do some kind of interpolation within that range, okay? But the high-level idea is still just to give you a value that is kind of in the middle. Make sense? So mean, like a weighted mean and the median, those are all ways to give you, say, if you look at a large number of values, you say, okay, what is the middle point, roughly, okay? And then another one, you may have heard of this term, okay? So the other is more about, like, say, the middle point, the mode is a way to say what's most frequent, right? Like, again, the idea is that you would say number of friends, right? So if you look at the individual values, so maybe it turns out like 127. That is the most frequently like value you see in this data set. Possible, right? So mode is really simple to say value that occurs most frequently, okay? But of course, sometimes depending on your data set, you may have a single value that is the highest frequency, okay? Or you may have, say, bimodal or like multiple modals. So that means you may have a few values that are frequent, okay? So think about, again, my annual income, like example. So depending on the population, you may see maybe a few modes, right? So maybe like there's some population, a subset of the population, right? They're more on the lower end, and they may see maybe, I don't know, it's hard to pick, 10,000 or like 50,000, right? And then you see maybe get to like a higher end, maybe say 1 million, right? Or a few hundred thousand. So those are the kind of like scenarios you tend to see. But again, you don't know from the beginning, right? Your goal in this process is to understand from your data. So you take your data, you do those analysis, now you have a better idea of what kind of data you have, right? Those are just ways of describing the general pattern, okay? So central tendency tends to tell you like what is the norm or the middle point or what is the majority, right? But then dispersion, sorry, I forgot to mention one more. So mid-range, so that's basically the average or mean and max. Remember, mean is the smallest value, max is the biggest value, average. That's again as a way of approximating, right? It may or may not be applicable if you have some extreme values, okay? Or you're like tilted, like skewed towards one end or the other, and that would skew your data points. But those are just all like a straightforward and actually pretty effective ways of measuring the central tendency. Okay, next we'll talk about dispersion, okay? So central tendency is about the norm, the middle point, right? The most frequent ones, okay? But then dispersion is about how different things are, right? Because you knowing that like annual income, even though I may have the mean value, right? But I know they're like either say everybody's close to the mean or it's a wide spread, okay? Right? So if you look at it, so typically if you do this as more like some kind of distribution, I'll just do it on the screen, right? So the way you look at the distribution is that like if it's like say a very like highly concentrated, you tend to see more like a spike, right? Everybody is very close along the mean value. But if it's more diverse, then you see a bigger spread, right? So that is what you're generally looking at when you're trying to look at the distribution of the values, okay? So range, as I said, right, so this is the difference between mean and a max, right? So apparently a smaller range means that the mean max are very close to each other. So it's similar, everybody's similar, right? A bigger range, that means a bigger spread. But that doesn't give you information about how things are spreading, okay? Just say mean and a max, right? So the quantiles actually gets a little bit more refined, right? So the quartiles basically say, okay, instead of just looking at mean and a max, I want to look at the middle point, right? 25th percentile, 50th percentile, 75th percentile, okay? And then I have my interquarter range, so that's basically the middle half, right? Remember, this is 50%, right? So you have, so this is 25, 25, 25, 25. So Q1 to Q3, so that's basically the middle half, okay? So now, again, depending on how big the spread, so your middle half, that covers half of it, and that's the middle, right? And then, of course, you still have the spread like towards the like two ends, okay? Another one, this is more of the mathematical calculation, okay? So now you have everything together. So many times, say if you just have a data set, we use this 5-number summary. So that just say, okay, I have a mean, I have a max on the other end, I have the mean max, I have the mean value, which is the 50th percentile, Q1, Q2, or Q1, Q2, Q3, right? So you actually have to have just using those 5 values, so you have a general understanding of the distribution of your data set, okay? Of course, sometimes you have outliers, okay? This is also very useful for you to have, actually, this is more like the first step. You start to see your outliers, right? So in a general distribution, you can say, okay, I tend to see some kind of normal distribution, right? But then when you have extreme values, so usually we're here using 1.5 IQR. So that IQR, remember, that's the middle half, right? So for the middle half, say it covers a range of, say, I don't know, like 10,000. And then I'll say, okay, if it's way beyond, because 1.5 outside of it, right? So that basically says, okay, it's quite different from the middle half, okay? And then we have the variance standard deviation. So those are terms I hope you're familiar with, okay? So this is just a way, again, like at calculating, right, the spread, okay? So here, just an example, this is a normal distribution, okay? So if you have a normal distribution, and then you have, so this is this is the mean value, middle point, right? Okay, and then you would have the sigma, so this standard deviation, so it's like 1 standard deviation out, 2 standard deviation out, and 3 standard deviation out, okay? So you're following your normal distribution, then you basically say, okay, if you're within one standard deviation, so this is the majority, you can see they're all very similar, right? That covers about like 60%, okay? And then you have like 2 standard deviation out, so that's about 90, that's 95, yeah, 95%, okay? And 3 standard deviations. So that's why we're using this property many times to see, okay, if you expect a normal distribution, then you want to say, okay, if I go out to like say 3 standard deviations, I should cover majority, right? 99%, 99.7% of the population or the expected values, right? All right, there are a few related terms, okay? So we talk about the basic ones. So far, we're talking about individual attributes, right? For each attribute, you can use this kind of statistical analysis to look at the central tendency, you look at the dispersion, okay? Covariance is another term. How many of you have heard of this term? Covariance, correlate, okay. All right, that's good. So this is basically when you actually compare across distributions, okay? So you have 2 variables, right? Instead of looking just one variable, the distribution, now you have 2. And now you want to see whether they're related. So the general idea is that, okay, if things are independent, right, then whatever you change and you change doesn't matter, right? So you may go this way, I go that way, so there's a bit of kind of randomized, okay? But if there's some relationship, okay, meaning that like if one is changing in this way, and the other one is always also either changing the same direction or changing the other direction. Okay, so that's what we're trying to measure with the covariance. Okay, so if you look at these terms, right? So this is the expected value A compared to A bar. A bar is the expected value for A variable A. Okay, similarly B. So that's basically say if A is higher than the mean of A, and B is also higher than the mean of B. Okay, so that means we're all changing in one direction. Okay. Think about the stock price, right? If one stock is going up, the other stock is going up, like relative to their mean value, baseline. Okay, or we're all going down. Or it could be the opposite, right? Whenever you go up, I'm going down. Okay, so that is what we're trying to capture, okay? And you can see if you look at the calculation, this is just a generalization of the variance because variance is calculated on a single attribute, right? And now if you're comparing 2, then you're basically seeing how they're, so this is really talking about the direction. Going one, like the same direction or different directions, okay? Related to that, okay, correlation. We've been talking about this quite a bit throughout the course, okay? So a lot of times when looking at the attributes, we care about the correlation because we want to see if one is related to the change of other. And that is particularly useful because if you know that things are correlated, then if you see one thing changing, then you have a way of knowing or expecting the other one changing in certain ways. Okay? So that's a high-level idea. Okay. So we use this term, correlation coefficient. Okay? So this is for numerical data. Okay? So if you compare to the previous one, it's hard to put, I didn't put them side by side, but the key difference with the correlation coefficient versus the covariance is that correlation coefficient is standardized, okay? So you're dividing by the standard deviations of A and B, okay? And because of that, right, we're measuring not only the direction of the change, but also of the relationship, but also the strengths of the relationship, okay? So strongly correlated versus weakly correlated, positive correlation, negative correlation, those are all things we're trying to calculate, okay? So using correlation coefficient, so here we can see these are just simple examples, right? It's clear. With real world data, you may see that as clearly, but you're trying to look for this kind of relationship, okay? So when there's no correlation, as you can see, right, they're going everywhere, right? But when you see like a nice positive or negative, so that basically says, okay, so in this one, temperature goes up, number of hot chocolate, that's the cells, goes up. And then temperature goes down, goes up, and then this goes down. So it's a negative correlation, okay? So as you can see, right, what we're trying to look at is whether there is a correlation or not, right? Whether it's a positive correlation or negative correlation, and how strong is the correlation. Okay, so those are all the terms we're trying to capture, okay? So this is numerical data. Can you do this with nominal data? Nominal data means I have categorical values. Can I take a majors and do an average? No, right? We cannot do that. So we need something different, okay? So this is what we call chi-square. Okay, so chi-square analysis, this is for categorical data. Okay, so instead of like taking the individual attribute values and trying to do some kind of like arithmetic mean, okay, we know that we cannot do, right? I cannot take a CS major, like electrical engineering major, and do a mean value. How do I define that, right? Rather, we're looking at the combinations, because you have one attribute with certain values, right? You have another attribute with potential values. For example, I'm looking at a major, right? So you may have a few different majors, okay? And then I would say look at maybe the degree program, like undergrad, like BA, BS, or like MS, MA, whatever. So you can see there are a few values here, a few values here. So naturally you have a combination, right? A student who is a CS major and a BS degree, or this is a student who is, like, say, physics major and a PhD degree, right? So that's the combination, okay? So what we're trying to do is that we take, so these are just the different categories, okay? So these are different classes, right? And then the R is the values, okay? And then we look at the observed value, so that means the combination, like how often do you see a student who is a CS major and like BS degree, right? And then this is expected value, okay? And then see whether there's some correlation. Okay, so I'll put this up, and let's look at a concrete example. Okay, so in this case, I have a population, right? I'm looking at two attributes, okay? One is about they like fiction or not. The other one is about play chess or not. Question one, are those attributes, like what type of attributes do I have here? Nominal, binary, ordinal, numerical. Binary, right? Yes or no? So when you have two binary variables, how many combinations do you have? 4. 2 by 2, right? So you have two possible values here, two possible values there. I'm looking at the combinations of 4, okay? So in this case, I have this matrix, right? I have, so this is like a combination. So this is true, like fiction, play chess. So that's what I'm seeing here. 250 means I have 250 like people in my population who like fiction and play chess, okay? So similarly, if you look at this 1,000 means that I have 1,000 people who don't like fiction, they don't play chess, right? So that's basically you're collecting the data, right? So the raw data, and these are the information you have, okay? And then we're calculating the expected values, okay? So remember, we have our formula here. So my expected value is about, if I look at this independently, right? So in my population, for example, I have 250 people who play chess, 200 who don't play chess, right? But they like fiction. So in this case, I have 450 of them, right, who like fiction. So that's my one way. So if you look at like fiction or not, so that's 450 versus 1050, right? But the total population is 1,500. So out of the 1,500 people, I have 450 of them like fiction. The rest don't. Similarly, if you look at play chess or not, again, the total population is 150, but since I'm dividing them based on play chess or not, I have 300 versus 1,200. Are we clear on this in terms of how to read this table? Good? So you have population. You're dividing them, right, using two different attributes. And for each attribute, you have the yes or no, right, true or false combination, right? Okay. Now I need to look at the expected value for each combination, each possible combination, okay? So the first one said like, this is about like fiction, play chess. So I know I have how many people like fiction? Number of people who like fiction, 450, right? And number of people who play chess? 300, right? So I want to take 450 times 300 divided by n. What is n? What's n? Yeah, how many people do I have? Which number do I use? This one, right? Okay, sometimes I see people adding this all together and end up at 3,000. Why? You're double counting, right? I take the 1,500 people, I divide them two different ways, right? So this is the way about, I have only 15 people together, 1,500 together. This is dividing based on like fiction or not. And this is dividing based on play chess or not. So the total number is 1,500. Okay? So once I have this, right, I can do my calculation. This is how I get my first one. So this expected value is 90. And I do the same thing for the other ones. So this is how I get 90 is the first one. 210, that's this one. 360, this one. And 840, this one. Okay? I have a value of 500. Okay? How do I interpret that? Okay, so I'm going to post this, like a link, but that's basically how you interpret, this table. Okay, wait, somehow missing one. Okay, so once you have this value, then you actually decide whether it's a high value or not. Okay, so I'm going to post in Canvas, there's a link. Okay, some of you may have seen this already. So this is the chi-square distribution table. Okay, or significance of value. So that basically says that given the total number of attributes you're looking at, the number of like dimensions or possible values you're looking at, so you need to have, if you calculate your chi-square with a value that is above the significance threshold, then it's considered significant, meaning that that is a correlation that is strong enough. Okay, so in our standard setting, if we do 2 by 2, meaning that I have 2 variables, each one is binary. Okay, then the significance threshold we have is 10. Okay, so anything above 10, like when you calculate the chi-square value, you get a value that's above 10, is considered significant. So in this case, I have 500. Is it significant? Yes, so that is a significant correlation. Okay, so we'll talk about this more later, but this is just like right now, I just want you to understand how to do this calculation. Okay, how to read the table, how to do this calculation. Okay. With that, now, this is actually an interesting question. Okay, we have been talking about correlation. So correlation basically means that, okay, things are changing together, right? Okay, so they're like, if there's something is changing, the other thing is also changing. So they're not independent. They're not random. Okay? Now, does correlation imply causality? No. Okay. Correlation means that they're related. Causality means that if A is causing the other thing to happen. Okay? So when you're being asked this question, like you say, okay, yeah, it doesn't look like it. So let me just use a few concrete examples. I found this on Wikipedia. I found it actually those are really good. So hopefully that'll help strengthen your understanding of this term. It's very important. Okay, in data mining, we have the tendency whenever you see something that's being correlated, you tend to use that as causality, and that is bad. Okay, first one. Sleeping with one's shoes on is strongly correlated with waking up with a headache. Reasonable, right? This is a reasonable correlation. Okay, I don't know what happened that you went to bed with your shoes on, but that usually means that you didn't get enough rest, or you were not in a very good state when you go to bed. So when you wake up, you get a headache. It's correlated, right? But this cannot be causality unless you have some kind of shoes that is really making you feel bad. Okay? So this is a correlation, not causality. Another one. The more firemen fighting a damage, the more damage there's going to be. Okay? So you can probably look up some of the related fire information. You can probably see that, right? How many people were sent to fight the fire? And then the total damage. Okay? Possible, right? The correlation is there. But then will you claim that the fire may actually cause more damage? I guess we wouldn't have that conclusion, okay? One more. As ice cream sales increases, the rate of drowning deaths increases sharply. Again, correlation. You can probably see that from your data set, okay? But if you're interpreting this as a causality, that'd be bad. Okay, so this really, again, gets back to our discussion about how you interpret your results, how you do your, take your data, how you do the calculations, understanding what those metrics mean, right? Because different metrics really you have different meanings, right? So those are, of course, extreme examples. You may say, oh, yeah, this is obvious, right? But in many of the real-world data mining problems, it may not be so obvious, okay? So just keep this in mind. We are calculating correlation, okay? Correlation may or may not be causality, okay? So you may be able to identify strong correlations through these calculations, but if you want to identify potential causality, you probably need a lot more. You need to control, right, many of the other variables to make sure that it is indeed this thing causing the other thing happening. Sometimes you just cannot get it. Sometimes you need to do some focus study to validate there is indeed some causality. Okay? So just keep in mind, right, correlation does not imply causality. Okay, so we have talked about like how to understand your data, right? Next, we're going to talk about a few graphical measures, okay? Because we have done like mathematical calculations, right? And we can do like, say, all kinds of like central tendency dispersion calculation to see. But many times, visualization is very, very powerful, okay? Here, like if I'm trying to look at dispersion, okay, box plot is widely used, okay? So it's a box, right? Basically, you use this box to kind of capturing the middle section, okay? So you have Q1, M, Q3, and IQR. So that is already captured, right? But also with the box plot, you can actually show the dispersion and extreme values, okay? So in my example here, right, so in this one particular, I have those dots because they are outside of my 1.5 IQR. Remember, we're using this 1.5 IQR as a way of measuring things that are way outside, right, of my middle range, okay? So in this case, right, if they're way outside, I actually show them like separately. So those are my outliers, okay? But I also use the whiskers, like so here, generally I just show up to 1.5 IQR or their actual value. So like it will not go beyond my mean or max value. So either they're within my mean max or they're within the 1.5 IQR, and then I have the outliers showing individually, okay? So this one, as you can see, right, then you can easily compare across branches, right? So I have different branches. I have the unit price, the kind of the products. Then you can quickly see that, okay, so which one has a higher mean value? Branch 3, right? So branch 3, this is the mean, and also has like a wider like variation, okay? So that's one box plot, okay? Quantile plot, okay? So quantile plot, as we mentioned earlier, like we talk about quartiles. Quartiles is only like 25th percentile, 50th, 75, right? Quantile is basically divided by 100th, right? So it also called percentiles, okay? So when you have this like quantile plots, same thing, right? You can take the different values and show like the quantiles. You can see they're all increasing, but they're different. So this is just another example to quickly visualize the distribution, right? You're basically picking a few sampling points, right? So as they say, 10th like a percentile, 100th percentile, 75th percentile, all that. So you can plot those like values, and then you have a visual way of comparing, okay? And then you can actually take, this is just one variable, right, one dimension, but you can compare two, okay? Because the idea is that if you have two distributions, if they're the same, then you expect to see them along this diagonal line, right? But when you have deviations, okay, above or below, then you know that like one branch, like in this case, for example, like branch 1 versus branch 2. So at this point, so like their median point here, then it's branch 2 is higher, right? Because it's above. Wait, above, that means the, yeah. So it's that the 50th percentile, then your branch 2 has a higher median value. Okay, so that's, again, just a way of comparing across different distributions, okay? One more, this one you probably have seen in many different settings, right, histograms, okay? So histograms, as you can see, basically you put the values into buckets, okay? So in this one, I'm looking at, let's say, percentage of cases across different months, okay? This could be criminal cases, it could be instances of something, right? So you may be able to see like something is happening more, so because these are frequency, right? So each bucket, the value compared to the frequency, right, within that bucket, okay? So as you can see here, you can quickly see maybe week 3, March, and then this one, July, tend to have higher values, and then February seems to be lowest, okay? So for example, we actually did an analysis of like people quitting their jobs, okay, and look at which months they're quitting their jobs, okay? So again, you may have a way actually with that histogram, you can actually quickly identify like when people are quitting their jobs, so which months are more popular for people to quit in their jobs, okay? those are just simple like plots, okay? One more, scatter plot, okay? This is related to the correlation. Remember earlier we were talking about whether things are correlated or not, right? So scatter plot is actually simple. You basically plot X and Y because you're comparing two distributions and whether they're related to each other, right? So you just plot the values. If they're correlated, you tend to see something like a positive, negative, right? Or this kind of up and down correlation. Or you can have something that's just random. So it's just a very direct visual way to show some properties of your data. Okay? So far, we're talking about just simple, right, plots. Box plot, histograms, scatter plot, quantile plot, QQ plots. Those are individual ones. You can do this in a more manual way, okay? But then, actually, data visualization is a much more powerful like tool, and actually, there's a whole domain in terms of visualizing data, visualizing results or patterns, okay? So if you search online, you can actually find many, many interesting like ways of visualizing information, okay? So I'm just want to give you a few examples if I want to show this, right? So this is individual, like a scatter plot, and then you can do this across many dimensions, okay? So you have a matrix, right? Then you can see like naturally they're usually like say correlated by themselves, but then you can see some attributes are more correlated than others, or some others are just not correlated, okay? This one, right? This is like a heat map, but you have the valley. So you can see you're using the height and using the color to highlight regions that are different, okay, or worse, further investigation, okay? Here, I'm just putting up some examples just to showcase that you can actually do a lot, okay? That's why also it's interesting and there's a value in just being able to understand your data, understand your pattern, and then be able to explain that, okay? So your goal is not to generate many of those plots. Your goal is to find different ways of plotting your data and your pattern, and then be able to showcase to other people, right? Say you may play with, say, hundreds of plots and come up with 10. Those are the ones you highlight. Say, okay, based on those, you see things that are particularly relevant or important, okay? All right, so hopefully, right, use this. We have actually a little bit of practice during the homework assignments, but then also for your course projects, think about how you can visualize your data, visualize your results, okay? All right, so we talk about data types, statistics. Then let's talk about the similarity and the distance, okay? So this is where you say you have your data, you kind of know the attributes, right? But more important now, you say, okay, how do I identify things that are similar versus things that are different, okay? Now remember, we have the objects, right? Each object is represented by some attributes. For example, I have 2 students. I want to compare. How do I compare to student, right? I need to look at their attributes, and I look at how I can calculate similarity or difference between those attribute values, right? And then I have a way of measuring how similar things are, okay? Or if I'm trying to like choose a vehicle to purchase, right? So I have individual vehicles. I have the make, model, year, and other attributes, right? Mileage or whatever, fuel efficiency. So then you can say, okay, I take all this together, and then I have a way of calculating similarity, difference. So you have a way of grouping things, and you have a way of differentiating things, okay? So that's what we're trying to accomplish. But apparently, it's different, right? Because I have very different data types. I have very different attribute types, okay? So starting point, how do you represent your data, right? So you can use this data matrix. That's basically just attribute values, okay? So in this case, you could use these 2 models. So that means your the rows are the objects, right? And you have the columns. Those are the attributes or features, okay? Simple. Or you can do one more step, and they say, instead of showing the raw value, I already do this calculated value. That's my distance matrix, right? So in this case, distance usually, of course, that should be 0 if you're the distance to yourself, because you're identical, should be 0, right? Another way to say distance should be symmetric. So that means distance from A to B versus B to A, well, we will say we will expect it to be like symmetric. But then you have the actual values already calculated, right? So here you're showing the raw data, the attribute values. Here you're showing the calculated distance values or similarity values, depending on what you're looking at, okay? All right. We're going to talk about quite a few metrics, but some of those you're probably familiar with. Okay. So for numerical data, we use allowed this by like some kind of distance function. Okay. So you probably have heard of like LP norm or Minkowski distance. That kind of depends on your p value, right? If p is 1 or 2, so you have the L1 norm, L2 norm. Okay? So those are all like mathematical calculations using numerical data, right? So this is for numerical values, okay? You can even do weighted distance, which actually we will get later, right? So you can say if your attributes, they're not equal. Some attributes are more important. You could potentially weigh certain dimensions more than others, okay? But the ultimate calculation is the same. You're basically looking at the distance across each dimension, right? Raised to the power of p, okay? And then you have the sum, right? So that's basically say you're different here, you're different here, you're different there. So basically how much difference you have along each dimension, you add them together, and that is the way you're trying to calculate the distance, okay? So quickly, if you look at some of the L1 versus L2, right? Manhattan distance, Euclidean distance, they're all different, even though they're all numerical values. You can take the same numerical values, but using different distance functions, they mean different things, right? So Manhattan distance, as you can see, you can only go up and down, like vertical or horizontal, while with the Euclidean distance, you go straight, right? So depending on your actual usage scenarios, like one may be more meaningful than the other, okay? So these are some key properties for like the distance measure, right? The distance value should be non-negative, okay? Should it be to yourself, should be 0, should be symmetric, right? And also this is the triangular inequality. So those are what makes the distance function like a valid distance function. But then we don't always have like numerical values, right? So remember we talked about the nominal attributes. So we say I have students taking different courses. I cannot take that and then just calculate the distance between, like how is the like, data mining course different from machine learning course? Maybe if you have a way of defining the distance. But generally the idea is that with the nominal attributes, we basically check whether they're exact match or not, right? So out of say maybe like you have, like each of you have taken say 20 courses, okay? And out of these 20 courses, right, like say between these two students, 10 are exactly matched, 10 are not. So that basically is a half, right? If you had a 20 out of 20, that is the highest match. 0 out of 20, that's the lowest one. So that's simple, right? So you basically look at the number of exact match versus the ones that are not the same, okay? There's another way to do it, okay? So you can use this as you actually converting this into a binary. So have you taken this course or not? Have you taken this course or not? So you basically get a binary vector, right, out of all the possible courses. And then you take that and say, okay, whenever there's a match, right, 1, 1, or 0, 0, then it's considered the same, okay? But with the nominator set here, we don't have a notion of a closeness. We only have a notion of exact match or not, okay? Now, binary, okay? So I've been talking about binary, right? So binary, of course, in the simpler case is exact match or not, right? Both are zeros or both are ones. Great, we're done, right? So we can compute, right? So this is QRST, so basically 1, 1 scenario and the 0, 0, that's a T, okay? So basically look at how the Q plus, so it's R and S, that's when they're different, right? Divided by all the possible combinations, that is the distance. When it's symmetric, okay? So what happens when it's not symmetric? What do we mean by symmetric or not? Okay, when you have a binary variable, for example, like if you have, say, a gender distribution, right? So it's mostly, like, say, male versus female, it's roughly the same, then it makes sense for you to do it this way. But sometimes if you're looking at a skewed distribution, for example, think about, let's say, like Amazon. Amazon has all the like customers purchasing different products, okay? They have millions of products, okay? They have probably millions of or more customers, okay? So for any product, what is the chance of this product being purchased? Small, right? So in this case, it's like if you have, say, 1 million customers and you have 1 million products, okay? For each product, how many purchases you would see from this 1 million customers? Probably a small number, right? So it's a skewed. So meaning that's what we call as asymmetric, okay? So when it's asymmetric, I care less about this T term because the T's means that it doesn't happen because if you think about the products, right, somebody purchasing a product, so the norm is actually nobody purchased it. And that'll be dominating. So this T value, if you're talking about a million products, a million customers, this T will be huge, okay? So instead, we ignore that T. We only care about R plus S, but then we're removing that T. You see this? So I only look at the QRS. So it's only is at least one somebody's purchased this. But I ignore this TT, like T, which is a 0, 0 form. Make sense? Okay? We are out. Okay, we have 1 minute. I'll just give you this example, and then we're done here. Okay? So here, this is like, I have a few like people, right? They have their gender information, then whether they have fever, coughing, they do a few tests with positive or negative, okay? So in this case, we know that gender is symmetric, but then fever, coughing, and whether they test positive or negative for the different tests, that's all asymmetric, okay? So now I'm trying to look at their distance, okay? So I'll just do 1 here. So Jack and Mary, Jack, 1 and 2, right? So only look at the positive cases, right? So it is, they are, let me see. So this is both yes, and then there's one that is different, okay? So there's one that is different here. That's the one I have here. And then if you look at the QRS, so Q is the 0, 0 case, right? I have 2 of this. And then this is the 0, no, let me see. R is like a positive and a negative. So I don't have any, so that's a 0 here. And then I have this 1, which is the NP case, okay? So that's how I get my 0.33, okay? We're out of time, so we cannot finish it, but this is just as more like you can do this as a quick exercise to see whether you actually can do the calculation, okay? Okay, so that's all for today. I'll see you on Thursday.
So, this is for which test is for this? It helps us find